A warm welcome to everyone for the today's presentation. My name is Ajith Kumar Sekar, and the senior engineer for IGBTs and silicon carbide MOSFETs from Infineon Technologies, Austria. In today's presentation, I'll be explaining about the benefits of .xt interconnection technology for power discrete power devices, specifically in cool-SiC MOSFETs. Before we jump into the benefits of .xt interconnection technology, let's have a look about the application and the trends in the application. When I refer to application, I specifically refer to industrial or consumer applications like the power tools, aircon, PV systems, and drives, and UPS, and so on. The inverter system for these applications are in constant development and demand for improved performance in response to continually evolving requirements. To be precise, higher efficiency, better reliability, cost reduction, size reduction, and so on. Specific requirements are mandatory for some of the applications. For example, working in harsh environmental conditions, over operating voltage, and over operating time, etc. To fulfill these requirements, Infineon's enhanced CoolSiC has come with an innovative .xt interconnection technology to have better thermal conductivity and reliability performance. Let's go into the objective of the .xt interconnection technology. As we know, the losses of the semiconductor chip causes the device to heat up. That means increase in the junction temperature. Whereas the junction temperature not only depends on the power losses, but also the thermal resistance of the package as shown in the relationship here. That means the solder technique in the package plays a crucial role in the system. Not only the thermal losses, even the power losses of the system. So what are the solder techniques or in the considerations? There are conventional soft solder, sintering technique, and our main topic of .xc interconnection technology. Let's have a look about the .xc interconnection technology and their benefits in the following slides. Infineon's .xc interconnection technology uses diffusion solder process. For the cool-SiC die attach, during this process, the cool-SiC die attach with special metallization is attached, as shown here in the left-hand side, to the package lid frame by applying high pressure and high temperature. By producing the high temperature is to melt intermetallic to form solder joints. By this, the conventional soft solder is replaced by the .xt interconnection technology. By the help of diffusion solder, that nothing but the .xt technology, we can reduce the solder thickness, which will result in the reduction of RTH, that's the thermal resistance. So as you can see here in the right hand side, the solder is almost 3 to 4 times reduced in the .xt technology. Let's see deeper what benefits this reduction gives. I said, due to the use of intermetallic, we can achieve higher thermal conductivity. That means better thermal resistance and better thermal impedance. The reliability performance is also improved during the assembly. What that means? It prevents die tilt and also solder bits. Also offers partially a void-free interface. In short terms, the Infineon's .xt interconnection helps to improve thermal conductivity and reliability performance. With this, the Infineon will have best-in-class cool-SiC .xt interconnection technology, and which is also available in TO247 3-pin package, TO247 4-pin package, and TO263 7-pin package, and more packages yet to come. Let's have a detailed look about each benefits of the .xt technology. The new cool-SiC MOSFETs takes advantage of the improved TO27 package using Infineon's .xt interconnection technology. This technology features an advanced diffusion soldering die attach process. The main benefit of this packaging technique is the significant reduction of the bond line thicknesses, resulting in a significantly higher thermal conductivity. This performances in the reduction of the junction to case thermal resistance as well as the thermal impedance of the device. As you can see here, the .xt interconnection technology shows reduction compared to the standard interconnection. That is nothing but the conventional soft soldering in both the thermal resistance as well as the thermal impedance. So in terms of thermal resistance, we see almost maximum of 25% reduction when it comes to the dot-XT interconnection technology. Whereas in the thermal impedance, we see almost 45% reduction in the dot-XT interconnection technology. So what that means? The improvement of the cool-SiC with this dot-XT technology will enhance the optimization for the system design with the cool-SiC MOSFETs. So for instance, let's consider an example. For instance, with a 1200 volt 30 milliohm cool-SiC MOSFET, the loss dissipation will be almost 35% less compared to the standard interconnection as shown here. So that means we can reduce, like we can dissipate more than 30% extra losses could be dissipated through this dot-XT interconnection technology. What that means in detail? That means 14% of extra current could be dissipated. That means higher output power in the same system size. Or we can double the switching frequency in a 2-level 3-phase full bridge inverter. We can reduce the passive size to half. Or we can achieve 10 to 15 Kelvin temperature margin. That means we can go up to 80% of the life extension when compared to the standard interconnection technology. Let's have the benefit of the thermo-mechanical stress. So as stated earlier, the dot-XT interconnection technology performs better with the thermo-mechanical stress. That means it increases the active and passive thermal cycling capacity. As you can see here, the dot-XT interconnection increases almost 2 times higher than the standard interconnection technique. What is the benefit of this one? That means no delamination between the mold compound and chips, and no bonding wire liftoff during this thermal cycling, and negligible solder voids in corners, and also no impact in the thermal performance. So with the dot-XT technology, by increasing the thermal cycling, we see much benefits compared to the standard interconnection technique. Let's have a look in the real-time application. So here I have considered 2 different applications for this comparison. In my first application, I have took welding machine as my first application, where I had compared Infineon's cool-SiC MOSFET with an external silicon carbide MOSFET from the competitors. So let's have a look in detail about the first application. Here, the solution is demonstrated with a 500 ampere power supply inverter design for a welding machine from a major manufacturer. Here, the power supply consists of a 3-phase full bridge topology inverter using 4 Infineon 20 milliohms 1200 volt cool-SiC MOSFET with a dot-XT interconnection technology, which is in a TO247 4-pin package. And the maximum requirements for the welding machines are given above. As you can see, that 40% of duty cycle, that means 6% turn on and 4% for turn off operation, and operated at a 50 kilohertz switching frequency with an ambient temperature of 40 degrees Celsius and 80 degrees Celsius of heatsink temperature. Let's have a look in the next slide about the output results between the Infineon's cool-SiC MOSFET versus the competitors' silicon carbide MOSFETs. As shown here, the chart shows the thermal performance during a 60% duty cycle. That means 6% turn on and 4% minutes of operation. Following the full bridge topology inverter arrangement, the continuous line shows the temperature of low side heatsink in blue and high side heatsink in orange. The dotted line shows the case temperature of an high side and low side MOSFET. And here you can see that it's clearly observed that the Infineon's 20 milliohm cool-SiC MOSFET performs with significant lower heatsink and case temperature, including lower power losses than compared to 20 milliohm silicon carbide MOSFET of the competitor. Also, you can note that the Infineon's cool-SiC MOS reaches steady state temperature after 5 minutes of system operation, as should be according to the heatsink thermal time constant. However, competitor's MOSFET never reaches steady state temperature, implying that power losses are still increasing after 6 minutes of operation. Finally, it is confirmed that the requirements of 80 degree Celsius maximum heatsink by the silicon carbide MOSFET discrete solution, even if the maximum ambient temperature of 40 degrees C is considered. So we can say that With our cool-sick MOSFET, we can show almost 6% difference in the lower side and 17% in the heat sink. Now let's have a look in the second application point of view, where I have compared Infineon's IGBT versus Infineon's cool-sick MOSFET in drive application. So here the topology is a V6 topology, and here you can see the supply input for this application. From this, you can say that the junction temperature is operated at the same junction temperature of the three different devices. I have took 40 ampere IGBT of a three pin and cool-sick MOSFET of Infineon 60 milliohms and cool-sick of 30 milliohms with the same package. And you can see at the same junction temperature, we can achieve more current with the cool-sick with .xt technology. On the other hand, with the same output current, we can have lesser junction temperature compared to the IGBT, which is the conventional shaft soldering. So these are the two applications that I have compared. And we have the research saying that the .xt technology performs better in terms of thermal as well as the reliability standards. So now let's go to the summary and have a look what we have seen here in the whole presentation. With the cool-sick MOSFET with the .xt technology, we saw that we can reduce the junction to case thermal resistance. That means we can increase the power density. We can reduce the thermal impedance between the junction to case. That means we can improve the reliability during the overcurrent surge events. And it can also have a better performance in thermo-mechanical performance. That means we can increase the active and passive thermal cycling. And due to the enhanced die attach process, which will increase the reliability performance overall. We can also expand the portfolio of the RDS on. With that, we can cover wider power range for industrial applications. With this, we can conclude with the best-in-class .xt connection with a simplified diffusion soldering. We can achieve the industrial standards of having higher power density, lower cost, and higher reliability, especially for industrial and consumer applications with our cool-sick discrete products. Thanks everyone for the presentation, for listening for the presentation, and thanks Bodos for giving me this opportunity for this conference. And once again, thanks.